All right, so in terms of the math part of solutions, so we talked in the previous videos kind of explaining what they are. But whenever we talk about solutions, we often want to know how concentrated a solution is, or how much of a particular, how much of the solute is actually there in the solution. So whenever we're talking about that, we generally refer to the concentration. So the concentration tells us how much of the solute is present in a particular volume of solution. Now there's a number of different ways we can report and talk about the concentration. So this particular video is going to go through a number of those different ways and look at the meaning of the different definitions for these concentration units, and then kind of use some of those to solve problems. Okay, so the first one we're going to look at here is weight volume percent. So weight volume percent is the mass of solute in grams divided by the volume of solution in milliliters times 100%. So that gives you the weight volume percent. The important thing to remember about weight volume percent, so the equation can be helpful that you're looking at down here, but more importantly is really understanding it. And that is to say, you want the number of grams of solute dissolved in 100 milliliters of solution. So if you look at this definition here that I have circled, that's an important way to be able to understand it. So, and the reason is you'll see it whenever we go to solve problems, but if I tell you that something has a 5% weight volume solution, you need to know that that 5% weight volume means you have 5 grams in 100 milliliters. And what happens is if people just memorize this equation down here on the bottom, and you try to plug in like 5% here, and then you try to do some other math, inevitably people get really confused because of this 100% number that's there. So that's why I always tell people, make sure you not only understand mass in grams divided by volume in milliliters and then times 100 to get it to a percent, but also to understand that a weight volume percent is basically going to be the number of grams in 100 milliliters. Right, so that's an important definition to know. So an example here, vinegar, the active component in vinegar is acetic acid. So if vinegar contains 5 grams of acetic acid in 100 milliliters solution, we would say you have 5 grams of acetic acid divided by 100 milliliters of the total solution times 100% would get you to 5%. So basically 5 divided by 100 would be 0.05. You multiply it by 100, that gets you to 5, and you put a percent on the end. So again, that's weight volume percent. Now, volume percent is going to be similar, except here there's not a weight in grams. So in volume percent, everything is in volumes. And what you see here, this V/V means volume percent, and it means you have the volume of the solute divided by the overall volume of the solution. And here it has both units in milliliters, and really it doesn't matter what your units here are for this as long as they match. So you can go liters over liters, you could do milliliters over milliliters, you could do microliters over microliters. As long as the units match, you'll be able to get to the same answer for the volume percent. But volume of solute divided by the volume of the overall solution. People will often get confused on this, because if I say, you take 50 milliliters of hydrogen peroxide, which is H2O2, and you add it to 50 milliliters of water. So what is the percent of hydrogen peroxide here? A lot of times, if people just look at the numbers, they'll do 50 divided by 50 and times 100, and that will get you to 100%, which is wrong, because the volume of the solution is going to be what happens when you mix the two together. Right? The total solution here would be 100 milliliters. So again, make sure that you understand what that means by solution. The solution is that mixture of solute and the solvent together. So in this case, the hydrogen peroxide, which is the H2O2, and the water. Okay, so let's do a couple problems here. So it says, what is the weight volume percent of a solution of 10 grams of lithium chloride and 750 milliliters of solution? So for this one, we have to know weight volume percent is weight in grams divided by volume in milliliters times 100%. You can type that in on your calculator. You would do 10 divided by 750, which gets you to 0.01333. Then you multiply it by 100, which gets you to 1.3, and then add a percent. Right, so 1.3%. And I did two significant figures because there's two significant figures in this number here. All right, so again, weight volume percent is the number of grams in milliliters times 100%. Now, this isn't part of the problem, but just to expand on this a little bit. So if this one is going to be our weight slash volume percent, W slash V percent, the other way we could write this would be to say that you have 1.3 grams in 100 milliliters, right? So 1.3 grams and 100 milliliters, that would be the same thing as 10 grams and 750 milliliters. But again, the definition of weight volume percent is the number of grams in 100 milliliters. Okay, so here's another problem. Saline solution used in IV drips like in a hospital contain 0.92% weight volume sodium chloride in water. So how many grams of sodium chloride are in 250 milliliters of the solution? So if you have an IV bag that's 250 milliliters, knowing that the concentration is 0.92% weight volume, how many actual grams of sodium chloride would be in there? So I've been mentioning kind of in the past couple slides, it's important to know that whenever you have this 0.92% weight volume, that means you have 0.92 grams in 100 milliliters. And this is important because this is going to serve as a conversion factor, right? So that's going to be our conversion factor right there. And that's going to mean if we know the milliliters, which we do, we can figure out grams. Or if we knew grams, we could figure out milliliters, right? But that number, or that conversion there, allows us to convert back and forth. So we want to know grams, right? It says how many grams of sodium chloride are contained in 250 milliliters of the solution. So we can start with 250 milliliters. And then we can say, okay, we know that there's going to be 0.92 grams per every 100 milliliters. And now knowing how our dimensional analysis works, right, we know that milliliters cancels with milliliters. Oh, for some reason my gram didn't show up there. 0.92 grams in 100 milliliters equals, so now you would take 250, multiply it by 0.92, and then you're going to divide by 100, and that's going to get you to 2.3 grams of sodium chloride. And that would be your final answer. And sometimes you can at least, if you, again, know the definitions, you should be able to kind of almost estimate this in your brain, right? 0.92 grams per 100 milliliter, that's close to 1 gram in 100 milliliter. So that means there'll be 2 grams in 200 milliliters or 2.5 grams in 250 milliliters. And then it should just be slightly lower than that, which is what our answer is. All right, so again, this can work out doing our dimensional analysis that we practiced back in previous chapters. All right, so next up in terms of concentration units is going to be parts per million. So parts per million is used to determine or describe the concentration when things are really dilute, really small. This is used in a lot of toxicology type studies where it's like, oh, the lethal or fatal levels of a particular chemical in drinking water is 1 part per million. Basically, you have 1 million parts of water, 1 or 2 parts of the toxic chemical, and that's how you express the concentration. And there's actually, if you look at the slide, there's a couple different equations here for parts per million. Up top here, the first one, it says mass of solute divided by mass of solution, and then times 10 to the 6, which is a million, or volume of solute divided by volume of solution times a million. So the idea here, you can do this in mass, and you can do it in volume. It doesn't matter which one you do, but it has to be the same. It has to be mass over mass or volume over volume. You can't do mass over volume. And then the other thing is the units. It can be in grams, it can be in kilograms, it can be in micrograms. The volume can be in liters or milliliters or microliters or any liters, as long as the units match for both, because our goal is to cancel out those units and then multiply by a million. And that's going to be what we define as parts per million. So here is an example. So you measure that there's 225 micrograms of DDT, which is an insecticide, in 1 kilogram of breast milk, right? And we know that DDT can accumulate in breast milk and can actually be toxic for nursing mothers. So, right, you can measure it, and we want to know if this level of DDT, this 225 micrograms in a kilogram of breast milk, is above or below the safe level, right? So how do you figure this out in parts per million? Okay, so first thing we do is we're going to notice that we have 225 micrograms and we have 1 kilogram. Well, we know that part per million is going to be mass over mass times 10 to the 6, which is a million. All right, so that's going to be part per million. Now the trick here, though, remember, is that our mass have to have the same units. So I have to convert both of these to the same units. You could convert everything to grams, you could convert micrograms to kilograms, you could convert kilograms to micrograms. It doesn't really matter how we do this. So what I'm going to do, since we have this number here, 1 kilogram, nice and clean, I'm just going to go ahead and leave that number alone. I'm going to convert the 225 micrograms to that 1 kilogram that you see there. All right, so let's start here. 225 micrograms of DDT. DDT. We know we want to get rid of micrograms and we want to go to kilograms, but I always suggest going to our base unit first, so micrograms to grams first. And we know that there's 1 million micrograms, which you can also write as 10 to the 6th, 1 million micrograms per 1 gram. Again, metric prefix from back in chapter 1. You need 1 million of the little tiny micrograms to make up 1 big gram. So now that is going to allow us to cancel out microgram and microgram. However, we're not done because we want to have this number in kilogram. And we also know that the conversion from kilogram to gram is going to be 1,000 grams per 1 kilogram. Gram is going to cancel, gram is going to cancel, and this is going to give us an answer that is going to be 225 divided by 1 million and then divided by another 1,000. So 225 divided by 1 million divided by 1,000 is going to be, do the math here, we're going to get 2.25 times 10 to the negative 7 kilograms of DDT. All right, so that's the same thing as 0.000000225. I just wrote it in scientific notation to save some room. Next up, to go to part per million. So part per million is going to be the amount of the DDT, so 2.225 times 10 to the negative 7 kilograms of DDT divided by 1.0 kilograms of the breast milk times 1 million. And that's going to be what gets us to the part per million. So 2.25 times 10 to the negative 7 divided by 1 times 1 million is going to get us to 0.225 part per million. And that would be your final answer.